Hello everyone, welcome back, and let's continue the discussion from the last video. In the last video we explained what is a Taylor series, and the basic idea was something simple, is that if we know the function, the value of the function and the value of the derivatives at some point, we want to calculate the value of the function at some different point. Okay, if this is x0, this is x, we calculated that, and what we saw is that f of x can be written as f of x0 plus f prime of x0 x minus x0 plus f double prime of x0 by 2 factorial x minus x0 whole square plus f triple prime of x0 by 3 factorial x minus x0 whole cube, and it keeps on going. It's an infinite series, right? And from the right hand side, what we saw is that it only contains the information from the point x0. So this is in some sense an idea of polynomial interpolation, is that you know some information at some point and you want to predict the value of the function at some other point. All right, and what we said is that if we truncate the series rather than taking the infinite series at some point, let's say at this up to order 3, then the rest of the terms will give me errors, right? Because I cannot predict the value of the function precisely if I do not take an infinite amount of terms. Okay, so now we want to formalize the error. We want to formalize with some theorem, and the name of the theorem is called Taylor's theorem. All right, so let's try to understand what it is. Let me write it down first. So let f be n plus 1 times differentiable on the interval a to b, and let f of n, I mean the nth derivative, be continuous on a to b closed if x comma x0 belongs to a to b, then there exists xi. So this is a Greek letter which is called xi, and you write it like this. Okay, so let's forget about it. Xi, which belongs to this interval from a to b, such that f of x is equal to sum over k going from 0 to n, and this is fk of x0 divided by k factorial x minus x0 of k plus okay, write it in the next line, plus f of n plus 1 of xi by n plus 1 factorial x minus x0 to the power n plus 1. Okay, so there are a couple of things to notice here. First, let's try to mark them. That f is n plus 1 times differentiable. That can be done, so I can take this up to n plus 1 because of this. Okay, and let fn, that means the nth derivative, be continuous in this interval, Fine. Now let's say that my x and x0. So x0 is, if you remember correctly from this picture, that x0 is where we know everything, and x is some number where we want to predict. Okay, so x and x0 both belongs to some interval from a to b. Then there exists another xi, there exists another xi which belongs to this interval, the same interval, but this is open, such that this is true. What does this mean? Let's try to understand that this is my f of x, so this is my left hand side of this Taylor series. And as I was saying, that look at this term, the first one. The first one is the first n plus 1 terms in the Taylor series. Why? Let's see that. So if you start from 0, then if you take 0 derivatives of a function, then it's the function itself. So the first term is just f of x0 divided by 0 factorial, which is 1, and x minus x0 to the power 0, which is just 1. So if you just get f of x0, which is the first term of the Taylor series. The second one is f prime or f1, whatever you call it, x0 divided by 1 factorial x minus x0. The second term is f2 of x0 divided by 2 factorial, and you have x minus x0 whole square, and you keep on going up till the term n here. Okay, so up till the term n, that means that you're taking first n plus 1 terms of the Taylor series, n factorial x minus x0 to the power n. But it was an infinite series, right? So what I was saying is that if I take the first n plus 1 terms, then I get a polynomial of order n, also of degree n, right? So you are approximating the function f of x with a polynomial of degree n with the first n plus 1 terms, and whatever is there after is your error. So your error is nothing but f of n plus 1 xi. So okay, f of n plus 1 xi divided by n plus 1 factorial and x minus x0 to the power n plus 1. So you can say that you can see here is that you don't know this xi. You don't know what xi is. You just know that xi is a number in between a to b, but you don't know what it is exactly. So you cannot find the error precisely. If you know the error precisely, then you can actually calculate the value of the function. But this is not the case, right? If you knew the function from the very beginning, then you wouldn't truncate it at some point. You would do it exactly. So if you truncate the series at some point, then what you can say when you're trying to calculate it in a computer, then you can say that your error will be of this form, and where you don't know this xi. But there's something to notice here, is that from this equation, what you can say is that xi is a number in between a to b. This is for sure. And if this is true, then you can find the upper bound of your error. Alright, so you can find that, okay, if my xi is in between a to b, what can be the maximum value of my error? And if you can find that out, then you can say, yes, okay, my predicted value by the polynomial is correct up to plus minus this number. Alright, so this is the idea of Taylor's theorem, is that you can calculate you can approximate the function with a polynomial of degree n, and your error will look like this, where it will take the n plus 1th derivative of the function, and it will be of order n plus 1. In x minus x0, the power will be n plus 1, and you will have an unknown xi here. All right, so So this sum, the first term, let me use a different color. This first term has a name. This is called the Taylor polynomial of degree n. Okay, so this is called the Taylor polynomial of degree n. And this second term is called the Lagrange form of the remainder. Okay, so let's work out an example and try to precisely understand what this theorem means. All right, so let's work out an example. So we all know that let's say f of x is sine x, then we all know that we can write it as x minus x cubed by 3 factorial plus x to the power 5 by 5 factorial minus x to the power 7 by 7 factorial, and it goes on. Okay, now I want to say that when I'm evaluating the value of sine in my computer, I will take up till, okay, let me use this, up till this part. Okay, so what I'm seeing from here is that this is okay, I can add a new term with a coefficient 0 because x to the power 6 is not there, and my next term is of order x to the power 7, so I can write this as p6 of x. Okay, so from Taylor's theorem, what I can say is that my f of x will be p6 of x, which is the polynomial, because you saw that the first term is the polynomial, this one, and the error looks like this: f7 xi by 7 factorial x minus x0 to the power 7. Okay, so I can write it in this way. I can write it modulus of f of x minus p6 of x is equal to modulus of f7, that means the 7th derivative, of xi by 7 factorial, and you have x minus x0 to the power 7. All right, now I can say that, okay, the difference between my actual function and the polynomial that I have kept till x to the power 5 here, what is the difference is the error, and my error looks like this. All right, now let's say that I want to calculate the value at x is equal to 0.1. Okay, and what is my f7 of x? That is the 7th derivative. If you calculate, keep on differentiating sine x, you will see the 7th derivative is minus sine x. Okay, it's not that difficult. Just keep on doing the derivative. You do it 7 times and then you get it. Okay, so now what I'm saying is that I want to calculate, and when you expand sine x like this, I guess you know it, that my x0 is equal to 0. All right, so my x0 is equal to 0, and so my f of 0.1, which is my sine 0.1, minus p6 of 0.1, my p6 is this green box, this one. The difference between them is equal to 7 factorial. 7 factorial is 5040. X minus x0, so x0 is 0, x is 0.1, so this is 0.1 to the power 7, and you have this modulus of this 7th derivative, which is just minus sine xi. Okay, now what I can say that, okay, I cannot say what the value of xi here, right? But I know that no matter what, sine xi is always less than or equal to 1. This is a bound on the sine function. So what I can say from here is that the value of f at point 1 minus the value of the polynomial at point 1 is obviously less than or equal to minus 5040.1 to the power 7, and I'm putting that equal to 1. That is the maximum possible error, right? If you calculate this value, this would be, so f 0.1 minus p6 of 0.1 modulus should be less than or equal to 1. If you plug in the values in a calculator, you will see that 10 to the power minus 11. So up to 11 digits, it will have no errors after the decimal point. All right. So we can really calculate it almost precisely for x is equal to 0.1 with the first 3 terms in the Taylor expansion. And if you want to know the exact result, the exact error at 0.1, the exact error is 1.983 into 10 to the power minus 11. So it's almost close. Okay, we have almost predicted it correctly, but this is the exact result. We can calculate it exactly because we know the value of sine function at 0.1. Okay, so there are a couple of things to notice here. Where is this error coming from? This error is coming from this series that we are looking here. This was an infinite series, but in a computer we stopped it at when x at x to the power 5. So this is an error which is different from what we did in the last chapter where we talked about rounding error. This is not rounding. We stop a series because we have finite amount of time. We cannot go on forever and let the computer run forever to get the precision. So this error is coming for the truncation of a series. Truncation of an infinite series. Okay, and this error is called truncation error. All right, and we will use this. We will have to face this truncation error along with the rounding error when we are using our computer and doing numerical analysis. I hope you understood everything, and if you have any questions, please ask me. So the main idea is that from Taylor series we get an infinite series, and what we do is that we stop at some point and we get a polynomial, and the rest of the terms gives me the error function, and the error can be estimated with some unknown xi, and this unknown xi we don't know it, the exact value, but we can get an upper bound of the error with this calculation. Okay, in the next video we will jump into polynomial interpolation with some technique. So this is the end of Taylor series. So the idea of Taylor series was that we know some information, we know the value of the function and some derivatives at a point, and we try to calculate the value of the function at some other point. So you're trying to extract your idea, you extract your information at some point and try to reproduce something at some other point. And these things are important in model building and machine learning, because you teach your program some information, you give it some information, and it gives you some prediction up to some error. All right, so this is the end of Taylor series. Thank you so much, and see you in the next lecture.